Hello and welcome to this episode of Night Sky News for October 2024 with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about what you should look out for in the night sky in the next few weeks, and then we chat about what's been happening in space news in the past few weeks. In this episode, we're chatting all about the latest award of the Nobel Prize in Physics for AI, and how Earth has ended up with a second miniature moon, and of course JWST's latest discovery of a distant galaxy where the gas seems to outshine the stars. There's chapter markers down here if you want to skip ahead to any specific news story, plus any scientific research papers I mention are all going to be linked free to read in the video description down below. This video is also sponsored by Trainwell, but more on them later. And without any further ado, let's kick things off and start by looking up. Alright, so last month we talked about the Orionids meteor shower, which this year the peak occurs on the night of the 21st to the 22nd of October from around midnight to dawn. Now the Orionids is usually a pretty good show. You have around about 20 meteors an hour typically streaking across the sky, so that's like one meteor, one shooting star every 3 minutes or so. But this year, on the night of the 21st to the 22nd, the moon will be just past full, rising just before midnight as well, before the peak, and that'll wash out all but the faintest of meteors. So you're probably going to hear a lot of hype in mainstream media about the Orionids meteor shower just because in previous years it's been very, very good. But the conditions this year, because of the moon, aren't going to be that great. So I'm not going to be making like a special trip for this. I'm not going to be getting up early, at like silly o'clock in the morning to try and spot any. So I wouldn't suggest you do either. We'll just have to wait and hope the conditions are better next year. The thing you should make a special effort to see though is Comet C/2023-A3, Tsuchinshan-ATLAS. Again, I spoke about this last month when we weren't sure how bright this comet was actually going to get because comets are notoriously unpredictable, but this comet has delivered. It reached its brightest back on the 9th of October, where it very briefly brightened to a magnitude of over -4.9, meaning it was technically visible during the day, with photographer Peter Horlek managing to actually capture it alongside the sun. A few of you sent me pictures that you managed to snap of it in the past few weeks, so thank you so much to everyone who shared those. As we reach the end of October though, it's getting fainter and fainter all the time now because it's getting further away from Earth, on its journey back towards the outer solar system. So it's starting to reach that limit of what you can actually pick out with just your eye alone. But if you do have a fairly dark sky, then have a go trying to spot this. It's going to be in the west just after sunset. Look out for that sort of like almost like smudge of something on the sky. If you're not sure if you can actually see it or not, maybe break out your phone, try and do a long exposure shot, or an even better camera and have a go at some astrophotography. Handily, Venus is also going to be in the same part of the sky, acting as a little bit of a way marker as you look towards that leftover glow from the sunset, maybe helping you find the comet. Venus is one of the brightest things in the night sky after the moon, so it should be really easy to spot and give you a good idea of where to look. If you see something towards the glow of the sunset that is very bright, odds are it's Venus. By the 4th and 5th of November, the crescent moon, aka the Toenail moon, will also have joined the party, swooping past Venus and also the much fainter Mercury closer down to the horizon. And they're both there all month and visible wherever you are in the world, but the best time to spot Mercury is going to be the 16th of November when it reaches something known as its greatest elongation. Because the problem with Mercury is that it orbits really close to the sun. So if you want to look at Mercury, you're also kind of looking towards the sun as well, which is why we only ever see it like just after sunset or just before sunrise. And so as Mercury orbits the sun, at some point in its orbit, it gets the furthest away that it sort of appears from the sun in the sky from our perspective here on Earth. That's at around about 23 degrees, which is known as its greatest elongation. What that means for us trying to spot it here on Earth is that it will be higher in the sky after sunset and stick around for longer before setting itself. It's still very close to the horizon though, so it's quite hard to spot, especially the further away you are from the equator. But if you're looking out for Venus, you might as well try and spot Mercury as well. And if you do like spotting the planets, well, the good news is that all of the naked eye planets are visible right now, and and they're all visible like this side of midnight, like the good side of midnight. So again, you don't have to get up at silly o'clock to see these things. So Saturn will be visible in the south as soon as the sun sets, with Jupiter rising in the east a few hours later, and then Mars a few hours after that. So it's also a really good time to appreciate what's known as the ecliptic, that path through the sky that appears to connect all the planets, which is basically the flat plane of the solar system. So it's the path that all the solar system objects take through the sky. Mars and Jupiter will also be photobombing the well-known winter hexagon of stars this month, which is not a constellation, it's what's known as an asterism. It's 6 of the brightest stars of the winter sky that sort of happen to ring Orion. So if you start in Orion with his left foot of Rigel, and then go down to the brightest star, Sirius, then up to Procyon, up again to the twins Castor and Pollux in Gemini, and just skirt past Mars as you go, up to Capella right at the tippity top, and then go down, this time just skirting Jupiter to get to the red star Aldebaran, which is the eye of the bull in Taurus, and then rejoin again with Rigel in Orion. And that's your hexagon. They're so bright that these 6 stars stand out far more than the constellations tend to do, especially if you're in a city with a lot of light pollution. It's a lot bigger on the sky than you'd expect, but once you've seen it, you cannot unsee it. And obviously with the name like winter hexagon, you can tell it's a real herald that winter is coming. It's going to be sticking around in our sky for a few months yet. So if you don't get clear skies this month, don't worry, you still got chance to spot this in the coming weeks and months. I think sort of seeing Orion and the winter hexagon, you know, like out of a car window and a long sort of dark evening, clear night journey is like a really nostalgic feeling for me. Anyway, I recently enjoyed some fantastically dark night skies on our trip to the North Cascades and Mount Rainier in Washington, the USA back in September, which was a very welcome bonus to our 2 weeks of hiking. We actually ended up walking over 195 kilometers with 9,800 meters of elevation gain over 2 weeks, which was something I thought I was really going to struggle with physically because I have quite a lot of joint issues on my right leg with like my hip and my knee, but I felt absolutely brilliant the entire trip, and it was all thanks to the strength training that I did with Trainwell, who are the sponsor of today's video. Trainwell makes strength training accessible for everyone at every fitness level. Their platform pairs you up with a real person, a real personal trainer who can tailor workouts for you based on your fitness level, your lifestyle, and your schedule. I had an initial call with my trainer, Chris, where I told her about my past injuries and my joint concerns that I thought would affect my ability to hike. And she put together tailored workouts for me each day that were organized around my work-life schedule and around what equipment I actually had at home. This strength training massively helped with my joint pain. I felt so much stronger on my hikes, and all that training did wonders for my mental health as well. Their app is so great. Like, it has your entire workout and it shows you like what exercise you should be doing and how you should be doing it. And it's always your personal trainer's voice that you hear in your ear as well, which is really nice because it gives you like a boost and a bit of encouragement. I also loved how you could play your own music during your workout and it would just like dim the level of the music every time your trainer would like chip in with like, next up is leg abductions, or like, you know, 10 seconds to go, like you've got this. And after each workout, I could chat with my trainer to let her know how I did or ask for any pointers or changes. Plus, thanks to that human connection with an actual person, that really held me accountable to the workout that I'd committed to doing. So after 2 months of training with Trainwell, I can really see why Forbes ranked it as the best personal trainer app of 2024. So to start your unique fitness journey with Trainwell, there's a link down in the video description below, or you can scan the QR code up here that'll get you 14 days free plus $25 off your first month with Trainwell. So thanks again to Trainwell for sponsoring this video, and now let's come back down to earth and chat about what's been happening in space news in the past month. First up, let's chat about the Nobel Prize in Physics that was announced this month, because after guessing correctly who would win it last year, I didn't want to push my luck this year. I wanted to be surprised, and surprised I was. I would not have called the prize going to John Hotfield and Geoffrey Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks. It was a curveball to say the least, but it was definitely a very well-deserved prize, and I'm sure you'll agree a very timely one considering all of the social conversation around AI at the minute. I think the reaction in Oxford Physics was a pretty positive one. So Geoffrey Hinton is very well known for his work with Google and his previous win of the Turing Prize, which is kind of like computer science's equivalent of the Nobel Prize. But John Hopfield hasn't had nearly the same recognition for his really early work setting up the field of machine learning. So what did they actually win for, and what has it got to do with physics? Well, if you have a machine learning algorithm or an AI, what you have is a machine, a computer, learning how to do a task. So in ChatGPT's case, for example, it's learning how to write sentences that make sense. And it does that by learning what words are more likely to follow other words. And how does that change based on different contexts or different questions you might ask it? So in order to do that, it's got to store a huge amount of information. And the way it does this is with a network, an interconnected network of lots of nodes that are all connected to each other. And so, for example, if we consider ChatGPT still, like each node is like a given word, and each connection and the strength of that connection depends on how likely it is that that other word over on a different node is likely to follow this word in a sentence. There are many different ways that you can go about trying to set up that network and also store that information in the network. John Hopfield helped develop what's known as the Hopfield method, and it uses the physics concept of spin to store that information. So every sort of atom and particle, like electrons and protons, will have either spin up or spin down, which turns them into sort of like tiny little magnets with sort of like, like north and south. And when they have those different spins, that also gives them different energies. And the different energy they have then kind of changes the behavior of that particle or that atom. For example, like it might behave differently if it encounters another particle or encounters some light or in a reaction from what spin up or down it is. In a Hopfield network, essentially your nodes have this property of like spin up or spin down. And so you can picture the network almost kind of like a crystal-like structure in physics. And to find the most likely output of this network, depending on whatever input you gave it, you have to minimize the energy by changing the spin up or spin down of the nodes. Geoffrey Hinton then built on that work to popularize what's known as the Boltzmann machine, which can then create new examples of the things it was trained on. So for example, new sentences from all the words and sentences been trained on, or like new images from all the images that the machine has been trained on. That's true deep learning, and that's why Hinton tends to be known as the godfather of deep learning. So although it might not seem at first glance that this year's Nobel Prize is actually for physics, especially since neither Hinton nor Hopfield are considered like pure physicists, they're more sort of like cross-disciplinary scientists working in lots of different fields with the applications of AI and machine learning. I think like the awarding of this year's Nobel Prize in Physics is just a nice little reminder that when you strip everything back, it's all just physics really, isn't it? All right, next up, there's sadly been a bit of a delay to the launch of the Europa Clipper mission that I spoke about in a video last month, this mission to one of Jupiter's moons, Europa, to investigate its habitability. It has a 3-week launch window that opened on the 10th of October. It was supposed to launch from Cape Canaveral in Florida in the US. I'm actually filming this today on the 10th of October, and as I film this, Hurricane Milton is still sadly tracking across Florida. So of course, NASA shut down the entire site for the safety of their personnel, and once the hurricane has gone over, NASA will assess the damage to any of the launch pads and work out if it is safe to try and stick to that goal of launching within this 3-week window. Because as much as we would all love to see this mission get sent on its way to Jupiter, the main priority is the safety of any staff coming back onto site, and of course the recovery of any of the communities that have been badly hit by Hurricane Milton. Heyo, Becky from the future here with some good news. Europa Clipper was successfully launched on Monday the 14th of October aboard a SpaceX Falcon Heavy rocket from Cape Canaveral in Florida after teams at NASA declared the site safe. It was so great to see the spacecraft separate from the rocket and the boosters and get exposed exposed to space for the first time. We also got confirmation that the final orbital insertion burn went really well and put it on that trajectory for Jupiter. There apparently was a vent failure on the spacecraft, but NASA reported that the propulsion system does all appear to still be working as planned. It's now got a journey of 2.9 million kilometers before arriving at Jupiter in 2030, where it'll begin its mission of working out if Jupiter's moon Europa is habitable to life. And Europa Clipper wasn't the only mission that launched this month, because the Hera mission also successfully launched on a SpaceX Falcon 9 from Cape Canaveral on the 7th of October. Now, Hera is heading to the double asteroid Didymos, which is orbited by Dimorphos. Names you might recognize if you've been around watching Night Sky News for a long time now, because Dimorphos was the asteroid that NASA's DART mission smashed into back in 2022 to test whether we could change Dimorphos's orbit around Didymos. And the DART mission was a success. DART changed the orbit of Dimorphos by 33 minutes, nearly 5% of its original value, whilst also casting a huge plume of debris thousands of kilometers into space. Now, we know that it was a success thanks to observations taken by both a CubeSat satellite that was deployed just before the impact, but also thanks to ground-based observations and observations taken with the Hubble Space Telescope of before and after the impact as well. And so because we know its orbit's changed, we can then work out, okay, well then how much energy did the DART spacecraft crashing into this asteroid actually transfer to the asteroid? How much did we change the energy of this asteroid, of this mass? Which is great knowledge to know in case Earth was ever in danger from another asteroid. We could then work out, okay, so for this asteroid that's maybe a slightly different size, how much energy could we transfer to it, and how much would that change its path through space, so much so that it hopefully would then miss Earth. Because you don't need to blow up an asteroid or send nukes to it like in all the disaster movies. All you need to do is just nudge it ever so slightly so that you mess up the timings of when it will arrive at Earth's orbit, and instead of impacting, hopefully just have a very close flyby of Earth. Which, it's great to know that we can actually do this with the tech that we have right now. But there are still some unanswered questions, like things we still need to know to understand this process a lot more precisely, to know what we're actually capable of when it comes to asteroid deflection. Like, for example, how big is the crater that the DART mission left behind? Or is there no crater because the asteroid just completely changed shape entirely? It just reshaped itself. So Hera is going to the asteroid again to conduct more experiments, including the deployment of 2 shoebox-sized cube satellites to fly closer to the asteroid, maneuvering in its ultra-low gravity to test what its new mass is and the mass distribution of the asteroid, but also doing like a crash scene investigation where it'll fly really low over the asteroid's surface to investigate if there is a crater left behind, but then also ultimately land on the asteroid to test the composition of the asteroid's surface, compare that to what we know was in the plume that was thrown up in the impact to figure out, okay, was it the same material, or was there only a certain type of material that was thrown out in the plume and everything else that was left on the surface was left there because it was heavier, for some example, and all that kind of information that we need to know in terms of like how much of an impact could we have on an asteroid if we were going to do this in the future. So a really exciting mission, all things considered, and it will take around about 2 years to actually get to the asteroid system, which, you know, in space exploration mission timescales, it's not that long to wait. Speaking of asteroids and Earth currently has a second mini moon with an asteroid that it has captured into orbit. Now, the internet seemed to go crazy for this, which I wasn't expecting at all. For me, this seems fairly like normal and obvious that this must happen all the time, and that if it does happen, it probably happens without us knowing about it as well. But if you are enamored by the idea of Earth having a second mini moon, the asteroid 2024 PT5 is about 11 meters in diameter and was discovered back in August of 2024. And if you plot out its orbit around the sun, you actually find that between the 29th of September and the 25th of November 2024, it passes close enough to Earth, and crucially at a low enough speed relative to Earth, that it will technically be temporarily captured by Earth's gravity. Meaning that for just under 2 months, Earth technically has at least 2 moons orbiting it. And if you're thinking that this path looks super weird, it's because the Earth is stationary in that graphic, and reality it's actually also moving itself and orbiting the sun. What's fun though is that the researchers who found this managed to publish the discovery in what's known as the Research Notes of the American Astronomical Society, a journal that was actually recently set up for like super short papers to report on like discoveries or even negative results. So it's great to see like that process is all working, along with the processes to discover these near Earth objects that, you know, could have been a risk to Earth. Although this one's size at about 11 meters puts it very low risk, especially on a global scale anyway. For comparison's sake, if you remember the Chelyabinsk meteor that burnt up and then exploded over Russia in 2013, that was about 20 meters across. And back then we didn't detect that meteor before it impacted with Earth's atmosphere. And that actually changed a lot of the processes by which we sort of go about keeping an eye on the sky, especially for these much smaller, fainter asteroids. So it's really comforting to know that after those changes have been made, you know, we did actually detect asteroid 2024 PT5, which was much smaller and obviously fainter. But it's worth saying that detecting these very faint, smaller asteroids is incredibly difficult, and we do only tend to detect them when they get very close to Earth. Next up, let's talk about the James Webb Space Telescope's latest discovery, the galaxy GS NDG N422, the light from which is like nothing we've ever seen before. It seems like the light being emitted by the gas in this galaxy is outshining the light being emitted by the stars. Now, this work was published this month by my colleagues at Oxford, Cameron and collaborators. And if you remember, I've actually had Alex on the channel before to chat about his research using JWST. So when I saw him last week in the office, I made sure to ask him about this one as well, because I was really curious about how they actually found this galaxy. Because yeah, sure, it's in what's known as the Jades field, where there's been like a big survey of that part of the sky with JWST to get really deep images to detect the faintest galaxies at the greatest distances. But that's just images. Not all of those galaxies have a spectrum where you take the light from a galaxy and split it into its rainbow to get a trace of how much light at each wavelength you have, which can give you so much more information about a galaxy, but it is very observationally expensive. Like, it takes so much longer to get a spectrum for just like a single galaxy as opposed to an image covering like hundreds of galaxies. So when I spoke to Alex, I was asking him, like, why did you have a spectrum for this one in particular that turned out to be weird? And they said what they did was they actually looked at the Jades field and picked out those galaxies that had really strange or really bright amounts of UV light that they were emitting, or at least it was UV light when that light was emitted by the galaxy, but it's since traveled through the universe, which is expanding, which has stretched those wavelengths out, redshifted them until they were the infrared wavelengths that JWST has now detected in them. So they picked out just shy of 20 of those kind of galaxies that were very, very bright in the UV and made sure to get spectra of those. And then when they were going through all the spectra that they had, Alex said that he was looking through them, and then this one popped up for this galaxy that they reported on in this study, and he was just like, that is so incredibly weird. What is that? Here is that spectrum for GS NDG 9422. And I want to give you some idea of, like, when you're looking at this with an expert eye, like, why does this look so weird? So as soon as you look at it, some things just jump out immediately, especially at this end of the spectrum. This is the UV light end of the spectrum. And you can see that you have a huge jump up followed by a drop. And then this sort of curved but steep ramp upwards. We don't see that in galaxy spectra, like at least in the like nearby universe. We do see the jump bit if you have a galaxy that's forming a lot of stars, but that curved ramp upwards is the thing that makes this whole section of the spectrum a little bit difficult to explain. Usually how you would explain it is that you've got stars that are then shining onto gas that's around those stars, and they're giving energy to that gas, which is causing the gas to glow, and you get this sort of shape in the spectrum. But from the amount of light they've detected here and the shape that they've got, to explain it in that way, you would need gas that it is at such a high density that has never been observed in the universe before, like orders of magnitude bigger than what's been observed in the universe before. And you would need the sort of just right, like geometric setup of where the stars and the gas were to get it to look exactly like that. So Cameron and collaborators went through all the other scenarios that they could think of that could also explain this spectrum of light they got from this galaxy. So that included the scenario I was just describing, that was what was at the top of the graphic there. But when they modeled for all of these different scenarios occurring, the ones that actually fit the data best, like fit that spectrum of light they've got from the galaxy and how they could recreate that spectrum of light with these different setups, were the ones where the emission from the gas, i.e. what's known as nebula emission, dominates. So either with the spectrum we've taken, we're only seeing the gas emission and it's like missed the emission from the stars in the observation, or whatever's made the gas glow has switched off in the past 1,000 years. So maybe it wasn't stars forming at all. Maybe it was actually a growing supermassive black hole that is now no longer growing, because otherwise we would see it in the galaxy spectrum. We would see evidence that that was there. So that when we look at it now, there's no obvious reason why the gas should be glowing. Or there's only a very few, very large, incredibly hot stars that are shrouded in gas that are bombarding that gas with so much radiation it outshines the stars at these UV wavelengths where we've got that weird turnover. And if it turns out that that scenario is what's going on here, then it means the ratio between like normal stars and then like these weird, very, very hot, very large, almost exotic stars is very different to what we see in the Milky Way today. And if you've been around, hanging out on my channel for a while, you'll have heard me talk about this before. It's known as the IMF, the initial mass function. And it's not the only result to have come to this conclusion lately either. A lot of papers that are looking at JWST data are saying, I think there might be a top-heavy IMF in the early universe, i.e. you form more of the more massive heavy stars in the early universe than you do currently in the universe today. Either way, whichever of these scenarios ends up being the correct one to explain this, each one is equally exciting. Because if you think about it, like either they've discovered the highest density gas seen ever in the universe blocking the light of stars in a galaxy, or they've witnessed the flickering on and off of a growing supermassive black hole on a timescale way shorter than usually seen, or they're seeing gas glow due to a population of exotic massive stars that we don't really have here in the local universe. Now, I say this all the time, but to understand this better and figure out which scenario is going on here, we need more observations of things just like this. Now, there are two objects that have been found a little bit closer to us in JWST data that do sort of look similar to this, but 3 galaxies isn't going to cut it. We're going to need to find way more of these things, if they exist, with galaxies behaving like this to whittle down which scenario is actually going on, if there's one that dominates in the early universe, which means the hunt in JWST data for things just like this is on. Alright, that's it for Night Sky News for this month. As always, if you see any space news stories that you want me to explain in a future Night Sky News episode, then send them my way over on social media, along with any pictures that you managed to grab of the night sky that you'd like to share. Don't forget to check out Trainwell and see if you can benefit from their personalized strength training. There is a link in the video description down below that will get you 14 days of free training with Trainwell. But until next time, everybody, happy stargazing. Right, well, I filmed the entire thing without audio, so let's do this again, shall we? It's probably gonna be less bloopers because I've already said this like so many times over. The first time I tried to film it, shooting stars per hour, streeting, nice and bright. Odds on are it's Venus. Odds on are it's Venus. Odds are it's Venus. Okay, which is the Sylvia Plath that all the planets take through the sky. There's a very loud plane going over, and I think it's just circling again. Here's everyone a little joyride in a plane, but I have to keep going. 5 to 2. Okay, I now have half an hour to get ready to leave, and I haven't packed yet. I'm just like, and I also need to make a thumbnail for this week's video, and I need to schedule that video, and I'm just like, I haven't eaten lunch yet. I need to feed the cat.